Hello, I'm David, just for the recording in case you've never seen my face. That's who I am. That's quite enough of that. I'm the coordinator of the Maths Learning Centre and the school of, whatever that school is called now, has brought me in to tell you about statistics as it relates to research. You guys, the medical students, have your research proposal task, and as part of that you need to discuss the statistics that you would do to analyse whatever data you might collect as part of that proposal. And also, as elsewhere, you'll have to be talking about research papers that you have read, and you'll need to decide whether the statistics that they do there are appropriate. And so these lectures are specifically about that choice of what statistics is appropriate to go with what research situation, and that's what they're about. And I'm teaching specifically that skill. And I will write a couple of exam questions to go in the multiple choice question part of your exam on specifically that skill and nothing else. That is the only thing I want you to learn, how to choose what statistics goes with what research situation. Okay, just so you know. That's the only goal. Everything else I tell you is gravy on top of that that might help you understand other things, but I have this one goal, and I will keep coming back to it as I go. This first lecture is called The Right Questions About Statistics, and it's called that because the best way to know whether you've got the right statistics is to ask the right questions. Right. So the purpose of statistics is to answer questions using data, and the question has to be specific and the data has to be specific in order for that to work. Statistics is not particularly good at answering general questions. Qualitative research methodologies are designed for that purpose. Statistics can only answer very specific questions, and often if you have a research question, you'll need to turn it into multiple, much smaller specific questions in order for statistics to answer those questions. And the data you collect has to be specific, usually quite small, putting people into a small number of categories or measuring numbers on them, or whatever the objects you're measuring are, don't have to be people. And they have to be very specific. They have to be specific things and measured in a specific way for statistics to be able to deal with it. But once you've got that, it's very good at answering questions using data. Before I move on, I should say, actually, if you talk to a statistician, people who run the theory of statistics, statistics is a way of coping with variation. It helps to find descriptions and explanations for how things vary using the information from the data. But what that means is that we can use it to answer questions in situations where things do vary, such as any research on people, because people vary. So if everybody was always the same, we wouldn't need statistics. But we do, because things vary. So just need to say that to keep my statistician friends happy if they watch this, and so they don't slap me and say, David, you're telling them wrong things. I've now said the right thing at least once. Okay, let's move on. I've already said the purpose of statistics is to answer questions using data. If you know what type of question you're asking, then you can choose what type of statistics you need. Later on, we'll talk about the data. But first, we're going to answer the questions. Oh, you should know that that handout I've given you has the most of the information that I've got on these slides. So, in case you're interested. There are four main kinds of questions you can ask that statistics can answer. There are a few others, but these are the main ones that are used in most research. And they come under these headings. They have, the red part is the purpose of the question, the black part is the kind of question that we're asking, and the blue part is what a statistician will call that area of statistics. So you have four purposes. It could be to describe, where the question is what's going on, to decide, where the question is a yes or no question, to estimate, where the question is what is this number, or to predict or explain, where the question is what's the formula. And I'll talk about them in a little more detail after I have mentioned this. Questions are about concepts. Okay, research questions are about ideas. So they might be about a single concept, such as what's the median number of chapters in a novel, or how much salt is there in an avocado, or what percentage of children finish all their homework. That's about one idea. Okay, one idea. But most research questions are about the relationship between concepts. So it could be, are science fiction books thicker than other books? So on the left we would have genre, And on the right we would have thickness, and genre is changing the thickness of books. Does getting more sleep affect a student's grades? So sleep on this side and grades on that side. Are women more likely to participate in volunteer work than men? So we have gender on one side and participation in volunteer work. Most research is about the relationships between things, and they're usually more complex than that, where you have multiple things affecting an outcome. Okay. Worth pointing out. So, some of your research questions, they're about general concepts, but you may be able to get them down into smaller, more specific questions, and they may be yes or no questions. Yes or no questions such as, is the median number of chapters in the novel equal to 20? Is your body temperature higher after a meal if it has chili in it? Does getting more sleep affect a student's grades? Are women more likely to participate in volunteer work than men? They are all yes or no versions of the questions that we had before. The reason why it's so important to know how to turn your question into a yes or no question is that statisticians have developed hypothesis tests, which is what p-values come from, specifically to answer yes or no questions. And these are the most common kind of statistical procedures you will find in medical or any other research is hypothesis tests, or some people call them significance tests. So p-values are designed specifically to answer yes or no questions, and I will get back to that in a later lecture, but that's what they're for. It may be that your question concerns a specific number that you're trying to find out the answer, what that answer is. So instead of asking is the median number of chapters 20, I would say what is the median number of chapters? How much higher is your body temperature after a meal with chili compared to one without? On average, how much of an effect does 30 minutes more sleep have on a student's grades? How much more or less likely is a woman to participate in volunteer work than a man? I'm interested in a number. How far apart are these numbers? What is this number? When your question is about how big a number is, then you're estimating, and when statisticians estimate things, they calculate confidence intervals. That's what confidence intervals are for, but I'll talk about them more in a later lecture too. These two questions are some of the most common kinds of questions that people use statistics to answer. A yes or no question of usually is there a relationship, and an estimate question of how strong is this relationship, can I put a number on that? Okay? And that's deciding and estimating. And I put them at the same level there is that they tend to use the same data. So you can almost always turn a what's this number question into a yes or no question, and vice versa if you pick a specific number that you want to compare to. So they're at the same level there. Above them and before them is the purpose is to describe. I said earlier statistics doesn't do a particularly good job of answering general questions, or this is the attempt of statistics to answer a general question. If your question is not specific enough to really know, and it's more of the flavour of what's going on, you're doing descriptive statistics. So how many chapters do novels have? It's a bit too vague for statistics to be able to pin it down exactly. So really you're asking, well, what are all the possibilities? What possibilities are there for body temperature? What sort of relationship might the amount of sleep a student gets have with their grades? You know, is it like a law of diminishing returns? You know, the more sleep you get, so up to a point you get higher grades, and then once you get past 12 hours of sleep a day, you're getting lower grades. So what sort of a relationship might that have? What sort of things might be related to whether a person does volunteer work? They're a bit too vague, and statistics doesn't do the best job of that. And what we do to try and begin to answer those questions is to draw graphs or graphs and basic numbers like an average or a percentage. So when you're calculating those and just saying, well, this is what we got, as an attempt to begin to say what's going on, that's descriptive statistics. All statisticians will always do this before they do anything else. Even before they've got actual data, they will draw a pretend graph of what they think might happen. Okay? And that's very useful to know because it helps you organise the way you think about statistics, which is what the next lecture is about, specifically about descriptive statistics. And finally, this is usually the ultimate purpose of most research, to predict or explain. Okay? So I'll give you some examples first. How can I explain a person's body temperature after a meal using their temperature before and the chili content of a meal? How can I calculate a student's grade based on the number of hours of sleep during semester? Now, there won't be necessarily the most precise calculation, but it will be, on average, I'll have a calculation that I can put in the number of hours of sleep and guess what their grade's going to be. How can I use a person's gender, age, income and religion to predict their chances of participating in volunteer work? You know, if I get all that information, I can look it up in a table and go, your chances are 20%. Okay, that's what predicting and explaining is about. And most research is about that. You want to say, well, if I do this to a person, they will get better. Or whatever it happens to them. Possibly, if this person chooses to make these life choices, then they have this percentage chance of developing heart disease. These are the sorts of things that most research is actually about. And in statistics, what we do is create a formula that you can put all the information in and it spits an answer out. And when a statistician does that, they call it modelling. And the formula we create is called the model. The process by which statisticians produce that formula is called regression. I mean, English regression means going backwards, but it doesn't have anything to do with the way the process works. It's to do with the story about how regression was what regression was first used for, as to why we have that word. But that's what they call it, regression. Now, these are the four main purposes. Very important to mention that all research has more than one statistical purpose. So you may have a big question of, I'd like to predict this outcome, but in order to answer it, you're going to have to first ask, well, what sort of relationship might it have, in which case you'll draw a graph. And then you'll say, all right, is there a relationship at all? And then you'll do a hypothesis test. And then you'll say, well, these numbers in the formula, what are they? Which is when you're doing estimating. And you'll have to do all of it. And each type of research, anytime you measure a different thing on the people or objects that are under study, you will have to do new statistical procedures. Now, this is why we have invented statistical computer programs, which can do all of these things in a flash, so we don't have to worry about doing 400 of them, because we can just tell it to get going and it will do them. But we have to do them all. Each one will have each yes or no question has its own p-value. Each estimate has its own confidence interval, and we have to do them all. So that's my first lesson, which is that research turns into multiple different questions that the statistics need to answer, each one separately. Right. I have a piece of paper here, and what I would like you to do when I give it to you is to look at the questions that I've put there, which are very specific questions, and choose which of these four categories it belongs in. The reason I'm getting you to do this now is because it's a very important decision that you need to be able to make. Because without being able to make this decision, you can't tell if you need, for example, a t-test or logistic regression. So you need to be able to make this decision. So that's why I'm getting you to do this. So please do talk to the people around you and see what you can come up with. Sorry. I'm going to stop you there, as much as you know, and it was good that you talked. I'm going to, whoa, maybe a bit far. Yeah, we'll do. All right, I'm going to ask the first 4 or so, and then I'll ask if anyone had any ones that were particularly confusing to them. So, I have a question. Does having chili in a meal affect your body temperature? What sort of a question is that? It's a yes-no question. Yeah. So it's a decide. Right, use green from now on. What percentage of people can distinguish between expensive and inexpensive wine? What am I estimate? That's what I'm attempting to do there. I'm looking for this percentage. It's a number. I want to calculate it. Can the majority of people distinguish between expensive and inexpensive wine? Decide. It's the same question, right? But it's the way that you've asked it, well, you would attack it differently. How much does taking a multivitamin change the chance of a heart attack? Anyone? Someone said estimate. Anyone got something different? Predict. Yes. I mean, really, I would go estimate. I'm specifically interested in a number which is how much this chance changes. In order to do it, I'm probably going to have to create a formula, but this is what my goal is, to estimate. Sometimes it's a bit hard to tell, which is why I'm saying, one of the reasons I'm doing this is so that you can point out that it is hard to tell, and that's why we have people like statisticians that you can go and talk to make these sorts of decisions. What percentage of women drink more than 6 cups of coffee a day? Estimate, good. What are the possibilities for how many cups of coffee different women drink per day? Describe. We haven't got a specific question yet. We don't really know if we want what percentage of them have a particular amount or what's the average. We don't have a specific number. This is the best that we can get. Now, most of the time, you will not generally write down formally a research question that has a describe answer. But sometimes you do. Sometimes you really do want to know, well, what are the possibilities? Okay. Good. Notice I haven't got many predict or explains yet because they're really difficult to actually write down as research questions. But here's one. What sort of general relationship might exist between childhood eczema and adult asthma? Well, at the moment, I haven't not looking for the specific formula yet. I'm just thinking generally going, well, what might happen? But this one, it has the word predict in it, which is fairly obvious. But, how do you predict a person's risk of heart disease using their smoking habits, their weight and their cholesterol levels? Well, it says predict. But really, the idea is that if at any point you're trying to maybe create some sort of formula, if you thought, well, a mathematical way of attacking this would be to do a formula, then that's a predict or explain. I'm not going to do any more of these. The rest of my answers are on my website, which you will find in your timetable-y thing that you have online. And those of you who are not med students, well, it's on my website, and that's how you got here anyway to this video. So it's right there next to the video. So you will find my versions of the answers to this on the website, and there will be a link to that soon enough that you will have. All right, back to the rest of the presentation. Talked about the question. Now, you know, it might be a little unsatisfying at the moment because I'm going, well, sure, I can choose whether it's supposed to be a hypothesis test or a confidence interval, but what does that even mean, David? And going, well, that's what the other lectures are for. But I have pointed out that you do need to just choose which sort of question you're asking in order to know what statistics you need. Well, you also need to know more about your data to choose what statistical method. Okay, suppose you've said, yep, yes or no question, totally need a hypothesis test. Which hypothesis test should I use? You know, it's about 200 of them. Which one am I going to choose? Even if I just choose out of the 10 most common, which one is it? Well, that's what your data tells you. It tells you which exact statistical procedure you're going to need. And there are three types of questions you might ask yourself. The first one, the big question is, how is the data collected? You know, how were the subjects chosen? To a statistician, a subject is whatever it was that you recorded information about. So they could be people, they could be petri dishes, they could be brain tissue samples, it could be universities. Some people do research and each university is a subject and it has information about that university. It could be basically any object on which you are recording information, that is a subject. You need to know how they're chosen. You need to know what was done to them, and you need to know when the information was recorded. So if you gave them a treatment, you want to know whether you recorded information about, say, their blood pressure before and their blood pressure after, before and after, or was it every 10 seconds with a probe stuck up their anus? Like, what was it? Okay, so you need to know how the data was collected and when it was collected. Now, this isn't just useful information for statistical purposes. Everyone needs to know this when you describe your research. That's why you have a methods section in a research paper. From a statistical point of view, when you do talk about how you chose your subjects, you should talk about randomness. Random selection is when you choose the subjects randomly from some population, or at the very least they're independent of each other. So even if you just had the ones that happen to turn up, if you can be sure that they're not directly related to each other, it should be okay. That's random selection, which is always good. If you can't get it, well, then you do the best you can. And random allocation is where you choose which subject got what treatment randomly. Okay, so instead of just doing the first 10 going into the control treatment and the next 10 going into the other treatment, you randomly choose who gets what. And both of them are important and make your statistics work better, because statistics is all based on probability, and most of the probability comes from the randomness. And so doing randomness makes a good thing. That's the last time I'm going to mention that during these lectures. I'm just mentioning it now because it is an important thing to consider, because sometimes it changes what you can do. And also, there are two main kinds of experiments. This is what statisticians call them. They're probably called something different in medicine or psychology or geology or whatever else you're doing. An observational study is one where the only thing that you did to the subjects while you were watching them was record information about them. So a survey, for example, is an observational study. But usually things done on newborn babies are often observational studies because, you know, it's unethical to, for example, get the women to smoke to see what happens to their newborn babies. Okay, so observational studies, all you did was record information about the people. In an experiment, you make a choice at least once to do something that might influence the outcome. You might make that choice randomly. That's okay. As long as you had some influence on what happened to them, then it's an experiment. It may be that all you did was put them in group A and group B, and you didn't do anything else. Technically, it's still an experiment because you did something that might influence the outcome. Because that could be a whole psychological thing where you told one group that you were doing something and you told the other group that you weren't, and then you saw what happened then. And you didn't do anything to any of them. So, you know, that's a great psychology experiment. Right. So they're the main things that you might want to know about how the data was collected. Randomness is important. Whether it's an observational study or an experiment, they're great things. But in general, having a good story of when the data was collected is very useful for a statistician or me who is close enough and is what you've got to know. So never skimp on telling people information about how the data was collected if you want them to help you choose statistics. The next thing is how much data you've got. Did you record lots of different things per subject? That makes a difference because It's harder. You need the more stuff you want to relate to each other in your formula, the more data you're going to need in order to create that formula. Do you have lots of subjects or only a few? Like, have you only got like 6 tissue samples, or have you got 50? Do you have 100 people or 1,000 people? That's important to know, because the amount of data you have changes how easy it is to pick up a difference. Okay, so if your question is there a difference? It's easier to tell if there's a difference with more data. And also you need to know if there's missing data. So if you're doing a longitudinal study where you're following people for 10 years, some of those people will just vanish and you'll never know what happened to them. That's important to know which of the subjects had that happen to them. Sometimes you have missing data in a survey where people just didn't answer that survey question. That's important to know too. How much missing data there is, and does it all line up, or does basically, if you took all the ones that didn't answer this question, all the ones that didn't answer this question, does it wipe out everybody? So you need to know. It's almost never necessary to throw everything away if you have missing data, and there is a whole research area for longitudinal data, a whole statistical methodology for that, which deals with missing data in that context. Other missing data, there's other ways of dealing with it, but you need to know whether it's there. And the final and most important thing is the variables in the data. So a variable is anything that you would write down about one of your subjects. It's called a variable because it's variable. Okay, not everyone has the same answer. There you go. So variables in the data, and anything that you would write down about them is a variable. It could be a word, it could be a number, it doesn't matter what sort of shape it is when you write it down. If you wrote it down, it's a variable. So there are these questions we need to ask ourselves before we can get to the statistics, and these are more important than any of those other ones in terms of making the decision, which is why I'm going to focus on them now. So you need to choose how to measure your variables. I'll talk about that in a second. You need to know if they're outcome explanatory variables, what type of variables they are, what distribution they come from, and whether they define groups or measurements. And I'll talk about each of those things in turn. So, as I said earlier, questions are about concepts. But statistics does not answer questions about concepts because concepts are too vague. Statistics needs very specific things in order to do its job. And so concepts have to turn into variables. You see, the concepts are nebulous clouds and the variables are nice, well-defined rectangles. So once you've chosen how to measure it, it becomes a variable. So for example, depression. How do you measure depression? Is it going to be mild, medium, severe? Is it going to be a score out of 50 on this questionnaire? What is it? Okay? How are you going to measure it? Are you going to measure it instead by some other method? So for example, measuring depression in rats, you count how much time they spend searching for food because the depressed rats don't spend as much time looking for food. So that's how you measure it, the amount of time they spent looking for food. So that's from the vet school, by the way. So how are you going to measure it? You need to make that decision, because once you've made that decision, it will make a difference to the kind of statistics you can do. All right, over on this side, these things are doing the explaining. These 3 variables here are supposedly explaining why that variable there has differences in it. And they're called explanatory variables, at least they are when I learned statistics. But of course, statistics is taught differently in every discipline, and so therefore they are also known as predictor variables because they're predicting, or independent variables. You may know them as independent variables as well. This one I call the outcome variable because it's the outcome. Not to say that these things necessarily cause that one to change, just that I'm capable of calculating the changes in this based on the others. So it's the outcome of my formula. That's why I call it that. But you might also know it as the response variable because it responds to the other things, or the dependent variable because it's dependent on the other things. I do need to say something very important about independent variables. They're not independent because they're independent of each other. They're independent because they're not dependent. Okay? They're not the 3 variables there might actually be related to each other. They're just called independent because they are independent. They're not the dependent variable. So just pointing that out. Which is why I call them explanatory variables, because it's really obvious what that means, at least to me. Right. So I have talked about how to measure the data, and I've talked about whether they're outcome or explanatory, and this is where I'm up to. This is not on any of those lists, but I do need to mention it. Because whenever I ask a statistician, hey, I'm doing a statistics lecture, what should I tell them? This is what they ask me to say. So this is what I'm going to tell you. This is how to organise data. Now, this year as med students, you're probably not going to actually collect actual data, but just for future reference, you need to know this. And it is useful because it does help you figure out how a computer draws graphs as well, and how to organise your thoughts about the data. So here is a pretend experiment where I'm trying to decide if chili makes a difference to body temperature. And I have these people here, and they have a gender and an age, and I've given them chili or not, and they have a temperature. And each person has a row in the data. And each variable has a column in the data. That's how to organise data. That's it. Okay, that's it. You can stop now, drop the mic, and it'll all be good, because that's exactly what you need to know. If statisticians, if you can do that and you go to a statistician, you will make them very happy. They can deal with everything else. All right. They also say this: please make it consistent. Okay, so if you've got gender, for example, and you've done it as capital M and capital F, sweet. But don't do a little m sometimes and a big M and a little m. Don't put an M with a space after it, because the computer's not clever enough to tell that they're not the same thing. It will treat them all as separate options for gender, and you'll get 7 different genders. Okay, so you need to be very specific and make it always the same way that you enter it, or the computer just won't be able to tell. I used to help someone with I helped her with her ecology, and she went and planted seagrasses in the South Australian Sea, and had seasons, and there was spring, and spring with a capital S, and spring with a space after it, and spring with 2 spaces after it, and sping. Okay, so you've got to be really careful to enter it always the same way, or your computer will get confused and all your data will be crap. So basically, do this. Right, moving on. Variables are the things that you record, and there are 2 main types of variable. Okay? And this is the most important bit of any of this for choosing which statistical process goes with what type of variables you've got. So there you go. I'm going to keep coming back to it. There are 2 kinds of variables. There is the numerical variable. That's what I'm going to call it, numerical. But some people call it quantitative. Some people call it scale. Some people call it interval. Depending on which resource you're looking at, it will have different names. And numerical variables are numbers. And I draw a little picture to represent a numerical variable. It's a little scale. I see an arrow on it. That's what my graph would have on it. It's a little axis for my graph. It's a scale on which to measure the numerical variable. Hence, that's why they're called scale variables. The other kind of variable is the categorical variable, which is generally words. Sometimes they're numbers. And some people call them qualitative variables, because what they do is they refer to the qualities that things have. But often they refer to the groups that things are in. That's what categorical means. It's about categories. And they're the 2 main types of variables. Now, if you've ever done statistics in the past, they will have gone down a little further and said, well, within numerical there is also continuous and discrete numerical variables, the 2 different flavours of numerical variable. And within categorical variable there is ordinal and nominal, 2 different flavours of categorical variable. That is more or less irrelevant to what type of statistics you're going to do. Okay? I do not care about these different kinds of categorical variable personally. I only care about categorical or numerical. So I'm not going to ask you any questions about whether it's ordinal or not. That's irrelevant to me. I want to know whether it's categorical or numerical. So just for future reference, say in an exam or something, just so you know what I'm not going to ask you. Okay, so these are 2 main types. You can tell the difference between a categorical variable and a numerical variable because with numerical variables, numbers, how far apart they are means something. So if you were filling out a CELT for my lecture today, and you said, like, on a scale of 1 to 7, from strongly disagree to strongly agree, how awesome was this lecture? Your 6 might not necessarily be the same as your 6. And the difference between your 6 and 7 is not necessarily the same as the difference between your 4 and 5. So because the difference between 2 numbers is not necessarily meaning the same thing every time, it's not really a number. It's actually a category. That's the idea. If when you do a subtraction between the numbers, it doesn't always mean the same thing, it's not really a number. And if you do a subtraction between the 2 things and it means nothing at all, it's not really a number. You can't do a subtraction between male and female to see how far apart they are. They're just different. So that's a category. Okay, so that's the idea behind the difference between them, because sometimes categorical variables are recorded as numbers, so you need to check to see if the numbers really are numbers. So I have an activity for that, because it's so awesomely important that you need to know how to do this. So it's the same deal. Choose which kind of... That's not enough. Which kind of variable have you got? Did you need another one? A spare? Did you need a spare one? Got some pros in the audience. All right, some pros have already gotten to the end of the whole thing and made some quick decisions, either pros or just committing early. So in order to, leave as close before 3 as possible, I'm just going to go over to the document camera. Before I move on, I should say that all of these research questions have been abstracted from things reported in the Body and Soul in the Sunday Mail newspaper. So I did not just make these up. Someone did actual research relating to these, not exactly the way that I've done it here. I've just used that as inspiration to create these research questions. But just so that I have done my citations correctly, Body and Soul in the Sunday Mail newspaper, the Body and Soul itself doesn't give any citations. So, yes. Okay. So, this is a variable I might write down about a person, whether a person can distinguish between inexpensive and versus expensive wine. Categorical or numerical? Thank you. Got 2 categories, yes or no. How often a person takes a multivitamin? Okay, I got 2 different answers there. Okay, so someone who said it was numerical, what's your thinking there? One, two, three, four. 1, 2, 3, 4 what? A day or a month or something like that? Cool. That could totally be numerical, right? Because you could ask them, how many do you take in, say, a week on average? And that would be a number. Did someone say categorical for that? I thought I heard someone say that. Well, it could have been. It depends on how you ask the question. If this was a survey and you asked them to tick a box as to, never, sometimes, often, that would be categorical because they're just categories. Even if you did a range of different numbers and they had to tick a box, you don't know which number it is, so it's still categorical. So it depends on how you ask the question, but if you can, you should try and make it numerical if you can, because that's got more information. The number of cups of coffee drunk per day. Numerical if you can. Whether more than 6 cups of coffee are drunk per day. Categorical. It's yes or no. All right, I'm going to skip a couple. How many dust mites there are in a square foot of carpet? Numerical. It's a number. Which experimental group someone was in? Number 9. What was that, sorry? Yep, categorical. Never numerical which group they're in, because they're just labelled by, you know, group 1 and group 2. They're just names. All right. The age of a mother at the birth of her first child. Sounds numerical to me if you can. I mean, if you can get, I mean, that information is generally recorded on someone's birth certificate and it's a proper number. Okay. What country a person was born in? Sorry? Categorical. I only mention this one because whether someone can smell asparagus is totally categorical, and it's a total thing. Not everyone can smell it. Yeah, so there you go. Personally, I can't smell anything, but not everyone can smell asparagus, and not everyone can smell the smell that asparagus causes. Asparagus causes the smell of your urine to change, and not everyone can smell that smell either. So.
Can the people who smell asparagus always smell that?
I don't know. It's a great research question. Okay. So, level of satisfaction, number 22, could be either. Now here's the problem. Level of satisfaction is almost always technically categorical, because the difference between 1 and 2 is not necessarily the same as the difference between 2 and 3. Okay? But most of the time, people actually treat it as if it was numerical. I'm just pointing that out. You'll actually have to make a choice. This is called a Likert scale, L-I-K-E-R-T. Not sure if that's how to pronounce it, but that's how I pronounce it. Good. My answers to that are on the website as well. That's a very important decision. If you can do that, yes?
If you had ranges for numbers, like it was like for how many cups of coffee do you drink a day, and there was like 2, 3, 4, 6, whatever, would that be categorical?
Yep, I'll repeat that question for those who are listening to the video and possibly who didn't hear. If you had ranges, if you said how many cups of coffee you drink per day and you had none, 1 to 3, 4 to 6, that's categorical, because you don't know what number it really is. It's a block. But good instinct. Okay. The last thing that you need to know, oh no, second last thing, we're nearly there, is the distribution of the numerical data. Distribution means how the possible values are spread out. And if I drew a height to represent how likely it is to be close to that number, I could draw a graph like this. If your data is approximately normal and looks roughly like a picture of a hat, sorry, not a hat, a boa constrictor with an elephant inside it, then a parametric test will be fine. If you've ever heard the phrase parametric test, if you ever read it, it's referring to the fact that you're allowed to use a normal you're allowed to assume it's a normal distribution. If it's skewed, like the top one, where it's got longer on one side than the other, or it's worse, like that one, which is called bimodal, you may have to use a non-parametric test. And if it's a Likert scale, a non-parametric test will probably not work, because most non-parametric tests are based on the assumption that 2 different people can't give the same answer. And if you're asking people satisfaction, totally 2 people can give the same answer. So you're probably going to have to treat them as categories and do a smaller number of categories, such as agree versus disagree. But no, most of this probably doesn't matter if you have a lot of data, where a lot is different for different situations. But most people say once you've got above 50, you can probably ignore the distribution and just go for the standard parametric version. I only mention that just in case someone brings up such things with you in the future, and I can say, yes, I did mention that, don't you remember?
Sorry, what's parametric?
Parametric means that your data looks roughly like that, and you're allowed to use a parametric test. The word parametric literally means referring to parameters, and a parameter is a number that describes the whole population. And that's not at all really what it's about. The parameters they're referring to are the mean and the standard deviation. So if your data, if your procedure is based on means and standard deviations, it's called a parametric test. And if it's not based on that and is based more on the order the data came in rather than the actual numbers themselves, it's a non-parametric test. And means and standard deviations are better for normal distributions. But I mention the words now so that you can say, hey, David knows what that words mean, I'll ask him. Okay, and finally, what the categories define. This is one of the things that distinguishes, finally at the end, you might have gotten yourself down to a specific test, and this will distinguish between two different kinds. So here's one way I could have done my chili experiment. You know, I've given everybody a meal with chili or a meal not with chili, and I've measured their temperature. I probably should have done before and after, but it's just a pretend experiment on my friends in the restaurant. Good thing it's pretend, because they probably wouldn't be friends with me afterwards. But this is what I'm going to do. And I'm going to, as I should, record their data like this. Every person has a row, and I've written down whether they had chili or not and what their temperature was. This categorical variable, this chili, which is yes or no, what does it do to my to my data? Well, here's a group of people who all have yes for chili, and that's their data there. And here's a group of people who all have no for chili, and that's their data there. What that chili variable did is split my big group into two smaller groups. That variable has cut my group into two groups, and that's why I've called it independent groups. Okay, there's an independent group situation where your variable has cut your data into independent groups, and each person has had the outcome of temperature measured once. Alternatively, I could have set up my experiment like this and given everybody a meal with chili and measured their temperature, and a meal without chili and measured their temperature. Now, if I recorded my data the way I should record my data, it looks like this. I've got a heading which says that they had chili, and then I record their temperature, and a heading that says they didn't have chili, and I recorded their temperature. That's how you'd normally record this data. I could have, however, organised my data differently and put everyone in the data twice. One row for when they had chili and one row for when they didn't, and sort of pretending that they're different people. But either way, all of these yes for chilies, they're here. And all of these no's for chili, they're here. But it's the same people, twice. That chili hasn't cut my group into two different groups. It's told me to measure everyone twice. So I haven't really got two groups, I've just got one big group twice. That's called a repeated measures situation, where every person, I've measured the outcome that I'm interested in, I've measured the temperature, I've measured it twice for everybody, I've repeated my measurements. And some people call it matched pairs. The pairs are not referring to the people, but to the measurements. I have two measurements for every person, a pair of measurements for every person, and they match because they belong to the same person. That's important. I will come back to that in a later lecture, but I want to mention it now, just for completeness' sake, where I have one lecture which contains all of the things that you might need to know in order to choose what statistics goes with what. These are all the things. The most important thing is the variables and the type of question, which is why I've given you an activity to do that today. Once you combine all of that together, you can know what statistics, and I like to draw pictures like this. In the top one, I have a single numerical variable, I want to know more about it, and I'm going to ask a describe question of, what's going on. And that would tell me that I'd probably draw, I don't know, a histogram. In the bottom one, I have a categorical variable, which is supposedly related to changes in a numerical variable. The categorical variable is defining independent groups, and my numerical variable is from a normal distribution. And I want to ask a decide question, a yes or no question. I know, based on my experience, that that is one-way ANOVA. All those bits of information, there were about 5 bits of information there, go together to tell me what stats goes with what. Now, unfortunately, they're not named, by any normal, reasonable system, because they're all created by different people, and some of them are named after the person that created them, and some of them are named after one aspect of how it's calculated, and some of them are named based on what they're trying to achieve. It's no good naming system, so you just have to learn them, unfortunately. But I'm going to teach you several lectures away from now the main ones and which picture goes with what. And that's my aim, for you to be able to choose what statistics goes with what. Either when you look at other people's research, you can say, yep, totally reasonable, that's the right sort of thing to do. Or when you're choosing your own, doing your own research and setting it up so that you can use the most common things. That's what this is all about. The next one I give, which is not till after the break, is about thinking about data in the way that statisticians do in order to really flesh a little bit this out and to draw graphs and graphs, if you're South Australian. That's what I'm going to do next time, and then I'll talk about each of the different kinds of statistical questions as I go, and then right near the end I will actually analyse a research paper, and I'll also have a request session so that if there's any stats things that come up along the way, you can ask, that I haven't already covered, you can ask about them. So that's what's going to happen for the next several months. Thank you very much. I'll see you soon.